Okay, in this first video after your exam, I'm sure you survived and came through it fine. I wanted to introduce uniform circular motion. So uniform circular motion, UCM, refers to a very specific kind of circular motion, one in which the speed is constant. So think about the following thought experiment. Let's say we're thinking about a car going around a track. So let's take a top view. Maybe it's a circular track. Circular track radius r. This is a top view. And so our car, a terrible looking car, looks kind of like this. It's got some wheels on it, of course, okay? And it's traveling around the circle in this fashion. So counterclockwise if we look at it from the top. So when we say uniform, the speed is uniform, but don't forget that as I'm traveling around the circle, my velocity is going to point tangential to my motion. Velocity, velocity. So, and I'll do one more over here, okay? So uniform means the speed is constant. It means the length of these velocity vectors are all the same, magnitude of them. But I hope you can see that the velocity is changing. If the velocity is changing, goes in a different direction, that means there's an acceleration. Okay? Now again, I don't want you to memorize this, although I think you'll get a lot of use out of it. When we talk about uniform circular motion, what we mean is that the acceleration points radially inward. So if I want to draw it on this circle, and each one of these points, what radially inward means, acceleration points like this. Over here, it points inward, and over here, it points inward. So think about Newton's first law. It said objects have inertia. This car would continue to go in straight line motion, constant velocity, if not acted on by an external force. So there's a force that has to cause the car to move radially inward. What could that be? Something to think about. That acceleration points radially inward, but its magnitude is a constant. Its magnitude is a constant. We usually call this the radial or centripetal acceleration. And in order to get uniform circular motion, that is constant speed, constant radius, it turns out, you can read this on your own, that the acceleration is v squared over r, the magnitude of it. Now again, its direction changes. I encourage you to do example 6.11, that's a pretty good one. But the idea here that I want you to take away, and I want you to be looking for, is in order to get this circular motion, this uniform circular motion, I'm going to need some kind of a force acting on, in this case, the car, to get its velocity to change. Think about this example. Okay? I like this one a lot. Think about a plane. If I have a plane traveling at constant altitude, not turning, not doing anything, then if I try to draw my terrible plane. Yeah, draw my terrible plane with the wings. Awesome, there we go. All right, cockpit, whatever, okay? If the acceleration is 0, that is if it's not turning, if it's not rising, or if it's not accelerating up or down, then there's force balance. If I draw a free body diagram, well, what I get here is I get some force from the thrust, which counteracts whatever drag force we might have. All right? And I also get some lift force due to the air traveling over the wings that is equal and opposite to the gravitational force. So the wings provide the lift force. Now imagine looking at a front view of the plane when it's banking. That is, the wings go from level to angled. We try to draw that. So I have fuselage, I have the wing, oh that's bad. Oops, let me draw it as I meant to at an angle. Wing, and the tail's going to kind of come up like this. Yeah, I know it's bad. I know it's bad, but the wings are angled. Okay? So look what's going to happen. If I draw a free-body diagram on this one, yes, I still get gravity acting downward. But from this view, when I can't see the thrust or the drag, look at what happens. A component of the lift force is angled. And that corresponds with the angle of the wings. So one of the principal ways that the plane turns is by banking its wings. I think you've seen this. That provides the force necessary to change the velocity and put the object into uniform circular motion. Have a look at, like I said, example 6.11, but don't forget, we're looking for the force. We're looking for the force to cause centripetal acceleration. Now, I don't like section 6.4, it's not a great section. And I will never ever in this class use the term, after right now, centrifugal. Ooh, it's hard to even get out. Centrifugal forces are fictional forces. We don't deal in fiction, we deal in fact. And so what we're going to do is we're going to look for the forces necessary to cause a centripetal acceleration. In this case, a component of the lift force. But I'm not going to talk about centrifugal forces. They're fake, but I'm not going to fixate on them too much. Okay, so spend a little time with the chapter. I think this is fun stuff. We're going to spend quite a bit of time on it, so make sure you get the most out of your reading. And as always, come chat if you